I'm Yoshinori. So I'm a production engineer at Meta. So I joined the company Facebook about 11 years ago, and mainly working on the database production problems like stability or efficiencies. And prior to joining Facebook, I worked on several companies, including MySQL. So today I'm going to talk about RocksDB at Meta. So RocksDB is a pretty big critical database backend at Meta, and how we are using that. So what is RocksDB? So RocksDB is an open source log structured merge tree. It's a LSM3 database. It was originally created by Google as a Reliabilities. That was more intended for front-end use case. And we forked that to use for database backends. So it's a library, and it's pretty easier to integrate, written in C++. And it's KeyValue LSM persistent store. And it supports a bunch of compression libraries like GStandard, LZ4, or Snappy or else. And it also has we added several backend features like background flash or compaction, so, which is pretty important for database. And which is open source, so you can download from GitHub and contribute to RocksDB ecosystems. So actually, RocksDB is used by a lot of companies, including from startups to big companies, and services companies to enterprise companies. So also not just OLTP type database providers, but also the analytics purposes it's used. And since this HTAP summit is organized by PinCap, so let me briefly talk about how TiDB, the TiDB uses RocksDB. So TiDB is, it's a distributed SQL database. And internally, it has a distributed KeyValue store called TiKV. And inside TiKV, there is a data store called Tablet. And inside Tablet, there are multiple RocksDB databases. And each RocksDB database is about relatively small. It's about 10 gigabytes, and there are multiple RocksDB databases. So essentially, it's a backend data files are RocksDB, and that's pretty important role for the TiDB database. So that's why I'm talking here today. RocksDB mission is reliable and efficient and easy to use storage engine for any workload and any hardware platform. So let me briefly talk about reliabilities. So you may know that the Meta is a social media company, and we don't sell RocksDB. So actually, we don't sell software. So I'm going to talk about several backend databases stories today, but we don't sell as a service for that. But we don't sell software, but we are using them in production. So that's very important for us to serve with high reliabilities. Like if we corrupt data or if we hit a huge downtime, then that's a big problem for our business. So making it reliable is a really important role. So that's what I'm focusing on day to day. So RocksDB use cases at Meta. So there are multiple use cases. So RocksDB was KeyValue Store, and it's more for OLTP use cases. So OLTP relational database is the most common use cases, but we are expanding the RocksDB use cases. So distributed KeyValue Store, and we started using analytics and machine learning. And recently we started expanding a use case for disaggregated storage. So today I'm going to talk about these use cases. The first one, let me start with the most traditional use case for OLTP database, which is called MySQL, the MyRocks, which is a MySQL on top of RocksDB. So this is also open source database we published. We first created the product in 2015 and started using production in 2017. So we use MySQL a lot on our Meta's Facebook, the backends. And one of the largest use case is called UDB, which is storing the users' activities like Facebook likes or comments. These reactions are stored in the UDB database, which is a MySQL database. Prior to using RocksDB, we stored in the default MySQL storage engine called InnoDB, which is a very popular B3 database engine. And one of the interesting architecture of the MySQL database is it has a plugin architecture. So MySQL has a lot of plugins, like the audit plugins or the thread pool plugins. So there are a lot of plugins, but the most relevant plugin is a storage engine plugins. So actually, InnoDB is one of the plugins for the storage, but it's by default, it's very widely used by default. But you can also add another plugins for storage. And we decided to use RocksDB as a plugin and implement it as a MyRocks. So the benefit is, so MySQL, there are MySQL clients, like a bunch of the CEO Java, the MySQL clients, talk to MySQL by MySQL protocol, and sends SQL statements that MySQL parser supports that. And these are not affected. So by just replacing InnoDB to MyRocks, then applications don't have to rewrite anything. And also, the MySQL supports replications, and the right side pictures shows typical of our MySQL backends. So a single primary instance and serves the write traffics and replicating to replicas. And when we migrated MyRocks from InnoDB to MyRocks, we first added replaced in a replica. So all primary and other replicas are running InnoDB, and we run MyRocks on the R4, the fourth replica. And since MySQL replication is not affected, so MyRocks could replicate from InnoDB, so without changing anything. And after MyRocks got stabilized, we flipped to the primary, and we could keep the InnoDB for in case of the severe instance. But eventually, we could flip everything to MyRocks. But these migrations were very easy for that. So major benefits compared to InnoDB is space efficiencies. So UDB is serving the social workloads. It's very constrained by space. So reducing the space was a primary motivation for that. So the major space differences came from the architecture differences between LSM3 and B3. So LSM, the fragments less often compared to B3. The B3, the fragments and using space often more than 50% to 100%. But LSM can tune more and it fragments less. So RocksDB's default file placement is called leveled. And with leveled, the default space overhead is only 11%. So it's much less overhead compared to V3. And I mentioned that LSM3, the RocksDB, supports natively about compressions. So it works much better compared to V3. And so by combining these, it saves more. And in addition to that, there are quite a few metadata. So RocksDB is KeyValue Store, and InnoDB also the low engines. And both of them have metadata, kind of transaction metadata, so which is 13 bytes in InnoDB and 7 bytes in RocksDB. In RocksDB, so actually most of the metadata are converted to 0 once they are not used anymore. Then 0, it's compressed very well, right? So any compression libraries can use almost 0 space for 0. So such optimization paid really well. So eventually we could save up more than 60% space compared to a compressed InnoDB formats, which are the huge wins for us. And big space efficiency wins means it writes less. So it means that you can potentially use more affordable flash drives because flash has write cycles. But the space efficiency was a big motivation for us. So in general, the LSM database is more efficient for space and the light performance and light amplifications, but it generally costs more for reads. And we spent a lot of time for improving the read performance. So as I said, the stability is hugely important for Facebook's Meta backend services. And especially what I paid more attention is better the worst case, the performance. So even if the workload is using very little CPUs or stable workloads for like 99% of the time, if the machine hits 100% CPU, so running out of CPU for 1 minute, then that's negatively affecting the user's experiences. So we wanted to avoid that. So we wanted to provide the better worst case, the performance, so that we can provide a good experiences for users' queries. So one of the example was range scans. So you can imagine that Facebook newsfeed, that most of the posts are shown in the descending orders of the time stamp. And when you click the post and see how many people that write comments, then the comments typically it's showed in the time orders, in descending order. So it's most of the, a lot of the Facebook, the UDB workloads are actually descending scans. And LSM RocksDB, it's less suitable for, less optimal for descending scans because of how it stores data backend. So we implemented the reverse byte-wise comparator that is comparing bytes in the opposite order. So to make a descending scans, doing internally it's doing ascending scans. So it gives like 25 to 30% the better the performance. And we implemented a prefix bin filter so that range scans can use that. And another interesting RocksDB or LSM constraint is if you delete a lot of records, then these deletes remaining in the SSD data files called tombstones, the delete markers. So this is also affecting the range scan performance. So we implemented a feature called deletion triggered compactions. So when there are many deletes, the RocksDB automatically triggers compactions to optimize them, to make that so provide a better read performance. Yeah, there are multiple optimizations, but primarily we wanted to provide a better read performance. So also, we invested quite a lot for memory stabilities. Like, so there are multiple memory allocators in the database or in the world that we primarily optimized with a MyRocks, which is a memory allocator, which is also maintained by Facebook. So with MyRocks, the integrations with RocksDB and MyRocks uses a much more stable memories. And we also recently implemented a memory charging feature that is providing a more flat memory usage, so regardless of how you use the mem tables like buffering. And also we limited transaction size so that large transactions don't cause state. And RocksDB is write optimized, but it doesn't mean that you can write a huge amount of data. So if you write like 10 million transactions per second, so something like a huge writes, then it's eventually causing stalls. So, so we invested a lot for better observability of the stalls and errors. So like number of L0 files counts or so. So giving the storing signals earlier so that we can optimize more. So there are a lot of RocksDB features for recently for the stabilized OLTP workloads. The key value checksums to detecting the corruptions and the failings instead of silently corrupting data. And user-defined timestamp is a recent implementation in the RocksDB, so which is a pretty good building block for distributed, consistent transactions. And memory charging is providing a better stable memory usage. And hyperclock cache is you can choose between the LRU cache and hyperclock cache. And the hyperclock cache is more optimal. So if the LRU causes a huge, big memory contentions. So we are providing the better experiences for more stabilized workloads. So these are the we have investments in the we did for OLTP relational database use cases. So next, I'm going to talk about distributed key-value stores, which is another major use case called ZippyDB. So unfortunately, ZippyDB is not open source, but there is a detailed blog post about it, so you can learn the details. So it's a distributed, strongly consistent key-value store. And it's a single primary and multi-replica models, and using RocksDB as a backend storage engine. So you write to the primary instance, then it has some conflict check, then write to transaction log in replicated over paxos and applying to replicas. Yeah. So let me talk about the key value store, the general key value store, the good points and limitations. So key value store is typically simple, so it's optimal for simple workloads, and also it's simple and it's pretty fast for writes. So compared to MySQL, so MySQL has a binary log and transaction log, like write-ahead log. So it's managing the two log. It's limiting write performance, but with the key value store, it's more optimal for writes. And it works well for simple data models. And for example, if you have an integer key and just one integer value, then it's simple to manage. So that's typically suitable for key value stores. But it doesn't work well all the time. So if the data management, the value structure is getting more complex, and if you need to manage them, it's getting more complicated and complicated. So if you have a record and put the array, it's A, and if you want to put B, then you need to overwrite that. And internally, it needs to write the whole images, AB and ABC, then you need to write the whole image again. But what if the value is like one big JSONs with 1,000 attributes, then or some of the 10,000 columns equivalent to MySQL. So it's if on the key value store, so when you fetch even if you just want to fetch the one attribute, then the whole value has to be returned to the client. And when you update something, then whole value has to be updated. So it's causing a pretty big overfetching and expensive read, modify, write. That is typical the key value store limitations. And there is a strong demand recently about machine learning field, and this is going to be this is causing bigger pains for us. So let me explain one of the common machine learning use cases at Meta, which is a recommendation system. So, for example, when you watch Facebook videos like Reels, then this history is written to log, but eventually we need to recommend the pretty good videos. So that's a recommendation system. And recommendation systems reads the data from a database called feature store. That doesn't have a original raw data because it's a huge. So we need some summarized data. For example, how many people watched my video for the last 60 minutes or so, or top 20 users who watched this video for longer than 10 seconds or so. There are several types of aggregations and transformation is needed from our log data. And we also need to update pretty often, because often the recommendation system needs very recent data, like sports events. It only lasts like 1 hour. Then its recommendation starts 1 hour later, then that's useless, right? So typically the aggregation has to happen very often. So you need often aggregating the data, then writing to a feature store, and the feature store is ZippyDB for our major use cases. And the common aggregation type is like last n, the sum or top k type. So the typical problem of the last n type, the operations, is suppose that there are think about last 5 operations. In the k, the key k has a values 1, 2, 3, 4, 5. And if you want to append the 6 for that, and the last n, which is a 2, 3, 4, 5, 6. And if you retrieve that and writing that, then actually the entire the last n has to be returned and updated again. So that causes a big write amplification that the network round trips. So we recently implemented the delta updates, which was composed by multiple building pieces. And one of the key enablers was RocksDB's merge operator, which is just writing deltas. And internally, we use Thrift objects. So Thrift is a default usage at Meta. So which is a Thrift object was stored in the RocksDB. And Thrift has a feature called Thrift patch that just storing the delta, the patches. And we store some minimal interpreters for expressing the column computation, like last n 5. So instead of storing the whole values, we just store the deltas and the instructions, so patch and last n. So these are what we do with for called a delta update and optimizing the write amplifications. So we have an internal service called Lodos, the RocksDB document store on top of ZippyDB. So it's primarily used for ML type workloads, so which is updating very often. And by optimizing these, significantly reduce the write amplifications and network bandwidth between client servers, and better the short-term space amplification and the write latencies. So this is one of the areas that we are optimizing RocksDB, and ZippyDB is a big user of the RocksDB and optimizing for some type of high write amplifications, the workloads that has a big value and only updating portion of the values very often. So with delta updates, the merge operator plays a pretty big part of that. There are several other ML-related features recently in RocksDB. So the merge operator was one example, so which existed for a long time, but recently we started using that for ML. And the wide column is a relatively new feature, which is published in the blog post recently, which is internally RocksDB's values. We can annotate the column names so that you can, inside the values, you can name the column A, column B, or column C, and just retrieve portion of the columns, which is a wide column feature. The bulk ingestion is we used, this is what feature has existed for a long time, and the MyRocks actually uses that for schema changes. But recently we started using for AI type workloads as well. So the benefit is bulk loading feature is if you know that original data is sorted by the keys, instead of writing to memtable and relying on the memtable flash or compactions, just RocksDB has an API to put to label marks, so the data files directly. Then you can bypass all the flash and compaction overheads, so that can just simply save time and save CPU resources and execution time. So that's one of the good use cases for ML workloads, since we often generate big files for that. And I mentioned that there's an original log, the video history logs, or several logs unstored. This is also a RocksDB. So there is a service called a distributed data store for logs and sequential data called a log device. So log device is open source, and this is also implemented on top of RocksDB. So there are quite a few areas that RocksDB is contributing to ML workloads. I'm very excited for working with them. So lastly, let me talk about our recent growing use cases about disaggregated storage. So as the CTO of PinCap talked today, so there are lots of the default use cases for data warehouse using disk aggregated storage, so separating compute and storage. And the RocksDB is actually input for OLTP use case. There is a growing demand for that. So especially for ML workloads. So with ML workloads, the workload is not really the uniform. So at Meta, so we have some specific hardware types with compute and direct attached storage. But not all workloads fit very well for the same hardware types. For some of the workloads stores lots of data and using a very little compute or using only compute for a certain time for that. And some of the operations need a big compute and with a little, very small amount of data. So not many services fit in the same type of hardware. So it's natural to separate compute and storage so that using a bigger compute for the expensive services and a small compute for people who use compute very less. So this is especially there is a growing demand for ML type workload because the workload characteristic differences. So we recently started investing in RocksDB for supporting a distributed file system, not just local file system. So there is a paper in Sigmod this year. So it's published, so you can download from this. So about stories about that. But high level, it's a really interesting and we are working well. And to adopting the OLTP workload, so there are two interesting challenges. One is a higher latency for I/O. So it's obviously, so it's a network storage, so I/O is increased. And the other is the I/O errors due to networks. So these lessons are a bit interesting. So let me talk a bit. So the higher latency, so typically it's about P99, the flash local attached flash read latency is about like less than 1 millisecond. But with distributed file system, the network file system, it's much higher. And it's pretty challenging if these I/Os happening when holding a record logs. Because holding record logs, and if it takes, say, like if it takes 1 second, then it may potentially block all other writes to the same record. And that's a problem. So yes, we are doing several optimizations like caching for the secondary cache for that. And the network I/O errors is, so when operating a local file systems, we really don't expect much for the I/O errors other than out of space, right? So, but on the network storage, I/O errors happens more often. So we changed RocksDB more about more robust against transient I/O errors. So like retriable I/O errors. So, and to make sure that we work that and we don't corrupt data for that. So we are starting using for that, and we are also investing heavily for making it much more reliable for that. So I'm excited for developing RocksDB for that. Yeah, so these are the stories of Meta, and as I said, so we are expanding the use cases. So RocksDB has been widely used across key database services at Meta, and not just Meta, but also the lots of open source ecosystems. And the major use cases are relational database MyRocks and distributed KeyValue Store, ZippyDB, and the expanding use cases across machine learning and distributed file systems. So we are excited to providing more features and robustness for these use cases. Thank you. That's it.